2 hits. Oh man, maybe not.
All right, well, I hit record, so you guys can go whenever.
Okay, all right. I don't have much of an update, to be honest, because the governance forum took up like 90% of my time over the last week. Although Kent and I did have some good discussions in the last couple of weeks. So maybe we can talk about that a little bit. But who? Maybe someone else wants to go first.
I'm happy to go. I'm happy to let Nate go.
Okay. Sure, I can go, and then maybe you can follow because I have some questions and thoughts about the charting fork trace stuff. So
cool.
So I spent the week so there was 2 things. The first one was that, in this like proof of concept of the sharding protocol that I implemented, there's no plot tool, but it was failing the fork choice atomicity asserts. So pretty much like, I was running the fork choice and then I was saying like, make sure the fork choice actually complies with what we want. And it was failing sometimes. And I couldn't figure out why. So I kind of started from the beginning and worked through the fork choice. And then it kind of turned into a bit more of like a general exploration of what fork choices we could kind of use this fork choice atomicity thing on pretty easily. So anyways, I'll explain the bug and then I'll talk about like some possible conclusions from my exploration. But the bug's kind of interesting. So essentially we're running a fork choice on some shard. Let's imagine, or, we keep selecting blocks, kind of, grabbing the greediest, the ghost roll, whatever. Kind of, if we hit a block that we think we should select, but this block is a merge block with a higher shard, then we necessarily can't select it. And the reasoning there is pretty much, pretty much makes sense. It's that, if that block was in the fork choice of the higher shard, then we would have started the fork choice from that block in the first place. So because we're not starting the fork choice from that block, we can't select it, and so we kind of have to move over it. And that's kind of the bug that I found. It's like a bit insidious and kind of interesting. But and then
you mean you weren't excluding them?
Yeah, I wasn't excluding them before.
That's a bug.
Yeah, it was gross. But anyways, so then it turned into a more general exploration of like what binary tree charting protocols we can easily enforce this like fork choice atomicity stuff on. And I guess I'll say the sentence that tries to like so like I like explored a bunch of them. There are like a bunch of them that like we can do it on that aren't really that interesting at all, right? Like, so we could, have it so every shard can have a merge block with the top shard and any combination of the above. We could have a fork choice, and in that situation, it's pretty easy to enforce the fork choice atomicity stuff. Another example is we could have it so, you can have merge my blocks on like only between symmetrical shards on either side of the tree. So switch all your ones for zeros and your zeros for ones. And then you start from the left or something, but not super interesting. But I guess it kind of seems like it works for any fork choice rule where, like, imagine we have, for each block, there's only one set of master shards, if that makes sense.
One set?
Yes.
I was thinking you'd say just one single one.
No, because, so here's an example. You could have a cycle of 3 as long as the set of master shards is the cycle. And so we kind of say, like, you have to, if you were going to merge mine a block, you have to merge mine a block between all 3 of them. And then it's kind of still very easy to enforce anything.
As long as you're not merge mining lots of pairs.
You can't merge mine any pairs.
Okay, you have to merge mine all 3 of them.
Yeah, exactly. So it pretty much works in any case where, like, the set of masters over you, the set of shards that can constrain your fork choice always have to act as one unit, which kind of makes sense.
Got it. Oh, that's interesting. Cool.
Yeah. Yeah, and that's pretty much it. I struggled for like a long time trying to.
Nice. Yeah, I always thought you just needed to have one parent, but I guess like you can have like a set of parents who always merge together.
Yeah, and the interesting thing is that those parents can also include any of their other children if they would like. So, for example, in our current binary sharding thing, we could have merge my blocks between 3 shards, and it wouldn't break anything at all. It'd be totally fine. Like we could have it between.
Oh yeah, between like a parent and and it's 2 children.
Yeah, exactly. So, which is nice. Yeah, the key there is that it also has to be like a union with the masters of the other shard, the other babies, I guess. And then there was one more thing I wanted to mention. Oh yeah, I spent a long time struggling with like how we can kind of have 2 master shards. And it's like the issue I keep running into, to try and say it in words, even though this might not make much sense, is that you can kind of come up with some weird like validity rules about where you're allowed to put blocks and stuff, but the issue is you kind of get, I'm calling it upfeeding, where like lower security shards kind of affect the fork choice of higher security shards. And that seems to be the only way to kind of like enforce this fork choice atomicity stuff. And in which case we kind of, that's not good. Obviously we don't want that. And also like, it's less clear where to put the validators if we actually were to start splitting things.
So, I mean, what's like the simplest example? One shard with 2 parents.
Sorry?
1 shard with 2 parents.
Yeah, exactly. So imagine 1 shard with 2 parents, and I want to be able to start my fork choice from either of the parent shards, and end up with the same fork choice on both shards. Here's the thing.
It's not going to work.
Yeah. It seems maybe possible if we have we run it on the left shard, the left parent first or something.
Now you're ensuring some kind of serialization.
Yeah, exactly.
Yeah. So if the left one followed the right one, and you follow both, then somehow I think it would be doable.
Yeah, but basically what you're really saying is that one of the parents is a parent of the other.
Yeah. So if you give me that, then I think I can make it work better.
Yeah. Yeah, that seems reasonable. But even then, I experimented that, and it wasn't like it maybe it works better, but it's not like in like the class of say like trivial.
No, it's not good. It's. I was just thinking like I could have eventual atomicity.
Yeah, sure. That seems reasonable. Oh, that's interesting. Yeah, I should start thinking about the eventual stuff rather than that. Cool. Anyways, yeah, that's my update.
Cool. That's a nice update.
Yeah, I spent most of my research time this week looking at load balancing and trying to basically do tree operations on the sharding, on like the binary sharding, in order to reduce the amount of traffic going through the different chains. So I was imagining, imagine if we have all the Ethereum accounts on the leaves, and they're calling to each other through the binary tree. We want to minimize the number of steps that everything needs to take when it's being routed around. And so I have this algorithm, which I'm, very confident defines the optimal load balancing for a tree of depth 2. And then my plan is to apply this algorithm at every node that is at least height 2. And so like every node in the tree will be load balancing the 4 nodes kind of 2 layers underneath. And basically this will kind of shuffle the tree in a way that where every kind of shuffle that is made is done to reduce the amount of calls going through the root node that the shuffle is kind of happening around. I get pretty okay performance improvements when I use like a uniform distribution of contracts calling each other. Meaning that I pick a uniformly distributed number for every pair of contracts for how many calls they're going to make. So maybe not the most realistic distribution, but I get something like 0 to 20 to maybe sometimes 30% reduction in the overhead in the root chart. 0 is kind of when it's already load balanced.
How much complexity is the calculation of the shuffling?
How
much overhead is that? Because that's going to eat into your.
Well, yeah. So it's not that bad because there's only 4 nodes there, but it's like n squared in the number of like leaves that I'm shuffling. But since I only shuffle 4 of them at a time, I'm not so worried about it.
No, I was just curious.
Yeah, no, it is definitely a valid concern, because like I am finding the kind of like global solution for the 4 shards, for the 4 nodes.
Yeah,
which does involve a little bit of a search. The greedy algorithm doesn't quite cut it.
Understood. Yeah, the reason I was asking is because in the R-chain setting we have there's heterogeneity in terms of resources, right? So you might have some nodes that are heavier on compute and some nodes that are heavier on storage and some nodes that are heavier on bandwidth and so on. And so load balancing is a little bit more complicated because you want to load balance with respect to those nodes that are better equipped to handle this is not for Mercury, but the ultimate goal is you want to load balance across those nodes that are better equipped to serve this particular namespace. So the namespace is going to have these metadata-like declarations in terms of quality of service. And so then the nodes are heterogeneous in terms of their ability to provide that quality of service, and then there'll be load on top of that. And then I think you also intuitively, I'm thinking that if a node puts up more stake, then that node should be under greater obligations to serve. So those are the different considerations that I've sort of so far thought about in terms of how to do the load balancing, and then I in some ways it becomes a cake cutting algorithm. Abstractly it's a cake cutting algorithm where you have different preferences with respect, some cake eaters want more nuts, and some cake eaters want more icing, and some cake eaters want more, of the cake part. And so slicing of the cake fairly amongst those, amongst the potential contributors, is a way to think about balancing the load.
Okay, but imagine if the nodes only were able to meet some single specification, then it would just be like a bunch of parallel load balancing problems.
Yeah, that's
it's kind of made tricky only because nodes are maybe able to serve multiple capacities or descriptions on node capacities.
That's what I was saying. That's what I'm saying. It gets a little bit more complicated, right? And so that's what spurred my question about the complexity, right? Because I can imagine the overhead here starts to eat into the benefits of the load balance. So I'm just
but the benefits should be high enough, assuming a kind of regularity.
Mm-hmm.
So Vlad, is there any security issues that you're worried about there, or is that something that you're going to think about later?
Well, so I'm only really worried about DOS. I have been thinking about how to kind of do the live action load balancing, in the sense of one moment the fork choice rule thinks those shards are over there, and then like the next it knows they're over there, and there's no consensus problems, right? And that I've thought about, and basically I reason that I can definitely do because the node that the root node of the node load balancing can synchronize it because all of the nodes that are load balanced are synchronized with it already. So just the binary tree makes it quite easy to identify like how it factors into the fork choice rule. The fact that like the shards are going to be kind of jumping around as they get shuffled. But it is something where I should probably have a proof.
Yeah, because I was thinking that if you don't, because this is about essentially validator to contract mapping, right? And so
Kind of, it's more like it's what I'm really doing right now is I'm moving shards around in the shard layout. So imagine we have like
I see.
which we know, which we like to note as like to like address the shards. And imagine like if instead we had like a map from binary strings to binary strings, and the fork choice rule always works like the original one, but there's like some indirection about which actual blocks are there.
I see. So I guess it's kind of like giving validators a partial control over how they can and they can only affect higher shards.
I'm not even talking about validators. I'm just talking about the data structure that we're replicating.
Yeah. So the validators don't really know which blocks they're working on, right?
I mean, it's not specified at this level of abstraction.
Yeah, exactly. So right. So you can always introduce an indirection.
So like the simplest first thing to do is to consider that we're making a consensus protocol that's replicating another kind of data structure, and then worry about the validator assignment kind of after the fact. And with load balancing, I'm changing the data structure from being like this sharded set of blockchains to a load balancing sharded set of blockchains.
Yeah. I mean, like, it's actually a nice idea. One of the Kent on our side, like we could do something like this. There's an indirection with respect to the names, so the validators think they're validating transactions on a particular set of names, but really at the end of the day, we then apply a map to go and figure out which names they really were. So there's a map from namespace to namespace.
Although for me, the way I'm thinking about it is like I'm thinking about it in terms of a map from a position in the tree to a node in a tree.
Yeah.
Kind of like I can by reshuffling pointers around, I can reshuffle the tree around without changing like the position of all the nodes. And then how kind of you can like represent things.
Yep.
So that it looks like a normal binary tree. And then but that will require kind of like change, so like and that kind of exposes the indirection. Ultimately it gets confusing because we kind of assume one of these maps when we draw the binary tree.
Yeah, well exactly. That's why it was so, like, even in our team we got into all kinds of silly mistakes because we were forgetting that you have these two lattices, and now there's the lattice of the power object of the total collection of validators and the lattice of the power object of the total collection of names, right? And then what you're talking about, like if I remap what you're saying into the RChain setting, then what you're talking about is you introduce a level of indirection between the namespaces and the validators that are assigned to them. So you can shuffle things around that way.
More like the namespaces and the names that are assigned.
Yeah, exactly. That's what I'm saying. So,
not the validators, but the actual like row calc names.
Yeah, that's right. So you factor the you factor the reassignment into just a name reassignment, and you can leave the validator to group assignment alone.
Yeah. I'll think about that later separately.
Yeah, exactly. Yeah. Yeah, it's a good idea. It's a really very clever.
I think it's natural from the point of view of just considering this to be a single consensus protocol that replicates a sharded data structure, and then as a first step.
Well, I mean, honestly, I think it has lots of applications to security.
What do you mean?
I mean that, like, it becomes harder to find out exactly, like, suppose I wanted to attack, like, so I want to pick off the weak shards, right? Or I want to attack, more importantly, I want to attack a particular set of transactions. So then if I can see that a particular set of transactions has been assigned to a relatively small validator set, then I can hack them. But if I don't know exactly which validator set goes to which actual transactions, it becomes considerably harder.
Sure, yeah. So are you thinking maybe you'll reassign the names as opposed to reassigning the validators?
Yeah, of course.
Cool. Yeah, that seems legit.
Cool. No, that's a really interesting idea, but it's cool. Thanks.
Yeah, no worries. Still trying to specify the sharded system without going into the whole fact that there are validators. One reason being that it'll also work in proof of work if I don't have to mention it. Not that it's like a very good reason, but it's going to be good for trolling Bitcoiners.
Yeah. Cool. Do we have any more updates?
So, Mike Birch and I have been working on the Archain state. And so, I was going to ask a few questions, I guess, maybe to both Greg and Vlad. But I read the regional calculus paper, or the one that tries to simulate it with PyCalculus groups.
Yes.
And I was wondering whether regions compose, or
remember, we're not interested in regions, because we're not implementing a functional language on top of this. So the regions, the whole region analysis thing is just to show that if you have a functional language with effects, then you can do a kind of region-based lifetime analysis on the resources, and that's great. And then you can implement that in terms of PyCalculus with groups. And that whole section we don't care about. It's just the name groups.
I see. So essentially, what we talked about on Monday was mapping the validators onto groups, right?
That's right. Yeah. So the only thing. So what we'd have to do is you have to decorate Roland contracts with name groups.
Yeah. And
right.
So if we're going to do that, might as well do that with adding the typing stuff.
Adding the what?
So if we're going to annotate Roland with groups, might as well also annotate it with types at the same time.
Yeah. So so again, what I was trying to do was to keep the bar with respect to the typing that we have to add for Mercury to be minimal. So what you can show, and that was sort of the whole point of pointing at that paper, is that you only need what are traditionally called sorts, the Milner style sorts, where you decorate the channels with what they carry, and the name groups. So we don't have to go to the full behavioral typing, just sorts and groups, and that's it. Yeah.
And so one thing I didn't quite understand was these groups aren't actually the scope of which isn't quite defined, right? For example, in Vlad's binary sharding scheme, it's well defined that a shard is some binary string of digits, and then as you go up the shard, you lose a digit, and then you get to that top shard, which is basically empty. But we kind of get to define the size of our groups, right?
That's right. That's exactly right.
And so I was wondering, and so do these groups compose?
Ultimately, they do, right? Because we know that the group is really just a name for a subset. And since we're talking about the or a sub-collection of the collection of all names, so we know that there's an algebra on that lattice. So yes, they compose.
So I mean, the way I currently see it is that you would annotate a contract with a group, but that's implicitly nested within like the top group, if that's a thing,
or it's nested within a group above it.
And so I mean, I didn't see any group annotations that looked like name in group in a super group, if that makes sense. But is that something that we need to think about?
No, you don't. No, that would break compositionality. So it's only at the time when you compose a couple of contracts that you have to worry about that, right? So when you're considering the par of some a contract that is the par of two contracts, right? Then the name, like when you go and do the group, it's actually in the rules. When you go and do the group of one of the contracts, and you go and do the groups of the other of the contracts, then when you go up, they're necessarily nested.
I see. So I think I missed that part. Yeah. Okay. So that's where the natural hierarchy will come from.
Exactly, from the pars.
Okay. Yeah. Okay. Then I think that's kind of that's it for my questions.
Cool. That's great.
Yep.
Are we possibly done 30 minutes early? Is there anything we wanted to touch more on?
Sorry, can I ask?
Yeah.
Go for it.
I was just going to ask a question about the load balancing thing.
Yeah, go ahead.
So are we moving shards? I blanked out a bit during it, but are we literally like moving shards around so that their parents change, I guess?
So it's a bit confusing. So what I'm doing is I'm assuming that I'm assuming that I have a routing system where a merge block corresponds to a route from one of the leaves to another leaf. And so it's going to like consequently lead to more merge blocks, right? So I'm assuming that like a kind of call is being routed from leaf to leaf. And
Okay.
so I set up this like matrix that describes the traffic across these different merge blocks and across the different shards. You can think of them as the number of merge blocks, really. If the traffic is higher, then we're going to need more merge blocks than if the traffic is lower. And then I'm moving the shards around, meaning that like instead of me merging with the same shards at all the time, the pointers will change and like different shards will be merged together at different times.
Oh, awesome. Okay, cool. Yeah. So
like at the end of the day, if shard, one talks off in shard 0, they should end up on the same side of the binary tree.
Okay, that's awesome. Okay, cool. It seems a bit like validator set rotation, like very slightly.
Yeah, I mean it's a bit.
Cool. Okay, cool. Yeah, I
still haven't really nailed the best way to represent the data structure. Right now, I have a map of binary strings that describe the position in the shard to a map of binary strings that describe the actual shard IDs. Meaning a map just from binary strings to binary strings, where it always maps like the same length string to the same length string.
This is all name management stuff, dude.
I'm not sure if that's the best.
So it can't move levels then.
No, yeah, I don't move in levels for now. For now, I always keep it a binary tree and I don't move levels. But I imagine that later, if we get good at this, we could have the tree structure change and have like, oh, look, one node here with like 5 children and like a tree that is like kind of maybe lopsided because like that's just the way the contracts call and that reduces the overhead.
Yeah, cool. Okay, cool. Yeah. I stumbled across I like wrote down, oh, what if we can do it like validator set rotation? It's cool. That's
because we kind of know how to do the 4-choice rule for an arbitrary tree, right?
Yeah, sure.
So any tree operations that we do, we can still kind of figure out how to do the 4-choice rule. But ultimately, the reason why this is all coming up is because I'm imagining that I'm replicating the Ethereum virtual machine. Or something like it using this blockchain. And so, maybe a good first step for us would be to like think again about integration with the Ethereum virtual machine.
Cool. I hear you. Okay, cool. Sounds cool. Thanks.
So if I understand this correctly, because I guess the difference between what I'm hearing from Greg and what I guess Vlad's doing is that, here with this load balancing, based on traffic analysis, you're shaping the way the data structure is composed. But with, you're constructing contracts in such a way that already have an assumed good, I'm going to put that in quotes, compositionality in terms of the sharding structure. Is that a good summary?
Yeah, that's right. That's pretty good.
So to me, the way that I would describe it is like Ethereum accounts have like a fixed identifier, and that persistently exists, and kind of they send messages between these kind of objects with names, and the shards have to manage the traffic between these persistent kind of persistently identified contracts, which can at any time potentially send a message to any other contracts, because we don't really know at the level of the consensus protocol what's going on. And so I kind of like passively look at the traffic analysis and react to it, changing traffic conditions, as opposed to knowing up front where everyone's going to communicate.
But you don't know up front.
I don't know up front at all.
No. What I'm saying is even in the R-chain setting, it's not that you know up front. What you know is that the behaviors that are going to affect some transactions between some accounts, and that's the contracts. And so rather than looking at the accounts, we're just looking at the behaviors that link accounts, and then that gives us an ability to sort of decide how to arrange the validators, or how to arrange the traffic, really is what's going on. So we're looking when someone deploys a contract, you kind of go, oh, okay, well, this is going to have this impact on the traffic now. So we restructure the traffic.
But when you say you can't really tell up front, you mean because the names might be created and passed around?
Exactly. Yeah.
But whenever that happens, you will reshuffle or make sure that the validator sets know somehow.
Well, the nice thing is you only have to reshuffle at deployment time. That's enough. You deploy a contract, and it basically, when you deploy a contract, it's like setting up a bunch of either new freeways or roadblocks or
Well, what if you
or
have
fleets of cars on the
What
street?
if you have a bunch of like execution, and then someone like quotes a process that was the result of like a whole bunch of execution that you can't really simulate ahead of time?
Again, you can detect that all in terms of the namespace analysis. Like you can
In the pi calculus, I mean, that kind of makes sense to me. But in the road calculus, I feel like I can just come up with random names, like, no problem.
in the pi calculus, you come up with random names all the time. That's what the new operator does.
Yeah, but the new operator somehow is different than quoting a process after.
Yeah, but the nice thing is that that's why you put the namespace declarations on top of the processes. And what that does is that forces you to only be able to legally quote certain processes as a part of a particular.
Oh, okay.
Yeah.
Right. Okay. I think I was running into this in some conversations that was happening this week. Okay.
Yeah. It's actually because they're like mutually recursive. Then when you constrain the processes, you're constraining the names, and when you're constraining the names, you're constraining the processes. In fact, I mean, just as a little bit of brain candy, one of the things that you can do is by putting, like, you can form subcalculi just by putting constraints on the names that calculi or the processes are allowed to use. So I've thought about going after complexity analysis just by putting in filters on the names. So I don't want to go too far straight, but Yoshida has this really nice factorization of the pi calculus in terms of this set of combinators, and then she has this amazing analysis where she says, if I eliminate this combinator, what can I express? If I put that one back in and I eliminate this other combinator, what can I express? She's got a really, really nice stratification of the pi calculus in terms of these basic building block behaviors. So we can do something similar in the row calculus, but it's a different way of stratifying. What you say is, well, you're only allowed to use names of this shape. And that gives you a different calculus. It's a subcalculus of the original calculus. And so by putting on different kinds of constraints on the shapes of names, you get different, different expressive powers. You get this little lattice of subcalculi of the row calculus, each of which has a different kind of expressive capability. But the interesting thing is that we get finer grained expressiveness because we can dial the structure of names in a much more fine-grained way. So the lattice is, has more points in it. So you can do all kinds of interesting complexity analysis that way. And the flip side of that is that we can do complexity enforcement. We can enforce the, with an example would be that we could enforce running time on a process. Now, if you take that too far, it becomes halting hard. But for a broad class of things, we can actually enforce running time on processes because they're only allowed to exchange. It's like a telomeres, right? When every time the process communicates, the collection of new names that it's able to access shrinks and shrinks and shrinks until finally they've exhausted the entire namespace that they could possibly grow, and so everything is kind of sorry, that's not running time, that's memory. So they've exhausted the total amount of memory that they have. You could do something similar with running time, where the length of the depth of the four comprehensions shrinks and shrinks and shrinks, and until finally you got no the length of running, the length of waiting for stuff is now 0, and so everything will terminate. Does that make sense? Did I lose people?
Yeah, sorry, you lost me at some point.
Okay, all right. Well, no worries.
Yeah, it happens.
Mutually.
So,
Okay.
are we ready to wrap up then?
Oh, just one last question. So, you know how when we're deploying contracts, we are restructuring, specific to Greg's model, when we're deploying contracts, we're effectively reshuffling the structure, like the data structure. But is there a proof on the fact that we won't get some kind of dominance cycle? Like, I don't know if you've
Yeah, there is yes, that's exactly what's happening with the typing judgment algorithm.
So it's always guaranteed to form like a consistent tree, if that makes sense.
Yes, that's correct.
And I mean, is that for free, or we have to actually like check that it's consistent with the past?
No, as long as you run that algorithm, it's consistent.
Okay, that's cool.
Yeah.
So, Greg, I have a question that I need to take it offline.
Sure.
Okay. So whenever you guys want to end this, we can roll.
Yep.
Cool.
Yeah, I think
Awesome.
we're good to go.
All right, guys. See you next week.
Guys.
Ciao, ciao.
That's it.